All right, in 4.3.1, we're going to talk about data points or data values, scatter plots, and really tying back into linear functions. So in the introduction here, one thing I really want to focus on is all the different ways that they show that slope can be written. So, right here in the middle, slope of a linear function is the change in the dependent variable divided by the change in the independent variable, or change in y divided by change in x. We all know that, okay? I don't think that's anything new. It can be written as delta y over delta x, which means change in y over change in x. A lot of times you'll see that in like science. That little delta triangle means change in. The slope between 2 points, x1, y1, and x2, y2 is y2 minus y1 over x2 minus x1. And the slope of the equation is y equals mx plus b, where the slope is m. It can also describe specific context, right? So change in miles over change in hours. A lot of times y'all do really good with calculating slope, but some of you don't do such a hard job connecting it back to whatever the problem is asking about. So that's probably going to be making this lesson a little bit challenging for you, because that's what it's all about, is connecting that slope to context, okay? Some of you are going to want to jump straight into the math, and that's not really what it's about. So key concepts, pause that, read those if you need them. First example here. The graph below contains a linear model that approximates the relationship between the size of a home and how much it costs. The x-axis represents the size in square feet, and the y-axis represents the cost in dollars. Describe what the slope and y-intercept of the linear model mean in terms of housing prices. Well, if we're going to do that, the first thing we got to do is find it. You got to calculate it. So I'm going to focus on these 2 points that we have here. Okay, 360,000 and 600, 120,000. So I'm going to write those 2 points down. So we got 360,000 and then 600, 120,000. Okay, so do my change in y over change in x. That means 120,000 minus 60,000 over 600 minus 300, which gives us a slope and m. That'd be 60,000 divided by 300, okay, which is 200. So that is your slope. So the next question is can we use that slope to find our y-intercept? So we take one of our points. We'll use this one, okay, and we're going to do 60,000 equals 300 times 200 plus b. Okay, slope, I did my x first, whatever, doesn't matter because multiplication is commutative. And what you're going to find after you solve that is b is equal to 0, because that'd be 60,000, and you subtract 60,000 on both sides, and you get there's you can kind of already look to see that, but you get the idea. So our equation for this then would be y equals 200x, and the question is, what does that mean? What is the context of this problem? So our change in y, so our m was 200 over 1, right? Change in y, so $200 per 1 x value, which is square feet. So in other words, it costs you $200 per square foot to build a house or whatever it is they're building in this problem. Okay? It's a linear function. You know what your slope is. You know what it means. So what about b? B was 0. What does that mean? It means if you don't build anything, right? If you do 0 square feet, it'll cost you $0, right? So it costs nothing to build nothing. So that would be the cost for 0 square feet. All right, no cost for no square feet. All right, and that's it. That's all you're asked to do on that problem. So we're gonna clear the ink there, move on. All right, example 2. A teller at a bank records the amount of time a customer waits in line and the number of people in line ahead of the customer. Describe the relationship between the waiting time of the people ahead of the customer when the customer enters the line. All right, so the first thing we want to do there is create a scatter plot. Okay, and we can see that this scatter plot pretty much has a linear function. Okay, it's fairly linear. And I didn't mention this in the last video in 424 and stuff, and I probably should have. But if you're trying to match a linear to a scatter plot, you want to draw a line that goes through all the dots as best as possible. If possible, especially if you're just estimating it, if you're trying to calculate an equation for that without using the calculator, then you really want it to go through some points. So for this one, if I were to, and I'm sketching this, so it may not be perfect, but you get the idea. If I were to do that, that's pretty close, right? That's a pretty solid linear line that goes through the middle of that data. And it actually hits a couple of points. I'm going to focus on this one and this one. Or I guess actually, yeah, we'll do that. That'll work. So to me, this first one is pretty obvious. It's 110. And the second one is a little less obvious, but it appears to be 10 and then 61. Okay, so if I wanted to find the slope of that, then I would do 61 minus 10 over 10 minus 1, which is 51 divided by 9. Right, and you get 5.6 repeating. Now, what does that mean? That's also, if you want to think about it, that's 5 2/3, which means if you think about time, right? This is what this means. So your average time that you're waiting. So this is time in minutes over, per person, right? Time per person, per spot in line. Okay, so 5 2/3, that would be, that means you're going to wait 5 minutes and 40 seconds per spot in line. Okay, that's what the slope means in the context of that problem. So the next thing you want to do is figure out what the y-intercept is, and does that y-intercept, make sense? Does it have good context in the problem? All right, so you would plug in your point. And we'll keep it as a decimal here, but so we're going to plug in 110. So 10 equals 1 times 5.7 plus b. So clear 10 minus 5.7 means you're going to get that 4.3 is equal to b. And that's, think about the context here. If there's 0 people in front of you, do you really have a wait time of 4 minutes? Doesn't really make sense, does it? If there's nobody in front of you, your wait time should be 0. Okay, so the context here doesn't really match. So you do need to be aware of what it means in the context of the problem. And since we drew the line, right, then we need to be aware that it may not be a perfect fit for a data set, because obviously this would be really the first point, 0, 0. Okay, because if you don't have anybody in line in front of you, you're not going to have to wait. Okay, so it's a relative fit for the data. It's not necessarily a perfect fit for the data. And you have to think about what that means in context. All right, stay tuned for example 3.